Hi, my name is Rami Ganem, and I'm a sophomore at the University of Kentucky. Today I'll be presenting about the synthesis of biofuels, which is the subject of my final lab report in technical writing. We'll go ahead and continue to my personal experience. Like I said, I'm a sophomore and I'm majoring in chemistry and chemical engineering, so I've taken a few chemistry classes over the past few years. I've had 1 year or 1 year experience as an undergraduate lab assistant under Dr. Knutsen's lab. She's a chemical engineering professor that I'll discuss a little further on. And over the past year, I've gained increasing interest in various social injustices, but the two that I've been most drawn to over the past year have included climate and food justice. Climate justice relates directly to biofuels as a lot of what has been happening with climate change and global warming has circled around our use of non-renewable sources or resources. Sorry. So biofuels present themselves in a unique opportunity as a sustainable solution to help reduce or ultimately eliminate the use of non-renewable resources. As you can see here, biofuels are liquid fuels that are produced from biomass, which can either come from animals or plants. As I said before, they'll have hopefully a tremendous effect on non-renewable resources, on helping eradicate their widespread use across the globe. Today, I'll be presenting about one potential method of synthesis called base-catalyzed transesterification. There are three main methods, but base-catalyzed transesterification presents itself as the most widespread use in industry and in the research lab. This is due to the fact of it being most economically feasible and having the least inherent risks, if you'd say. The purpose and audience of my lab report are pretty unique. The purpose will be to validate this method of base-catalyzed transesterification in producing biodiesel. What that means is I'll design an experiment to ensure that the base-catalyzed transesterification method actually yields biofuels, which will be essential going forward as if industries and other organizations are using this method and it doesn't even if it doesn't even yield biofuels, then why are we doing it? I'll be writing this in a lab report style, so I'll be presenting experimental data that I have obtained, which will be exciting. And this will all be addressed to Dr. Barbara Knutsen, who I mentioned earlier. She's a chemical engineering professor at the University of Kentucky. She serves as my research advisor, and one of her points of emphasis in research is energy sources. So biofuels relate to her field of study directly. So to date, I have had a lot of progress, thankfully. It's been going well. I've conducted my experiment completely and I've analyzed my data. That included obtaining time at a HNMR machine, which is a fancy term used to describe characterization of the compound. Basically, that justifies that what we produced is biofuel. So I've analyzed that spectra and it's shown later in this presentation. Alongside that, I was working on my rough draft of the lab report, and now it is completely done, and it just requires rigorous revision and proofreading. So I'll present some preliminary findings here. The oil number refers to what oil I used. So I tested 3 different oils, which were canola oil, vegetable oil, and olive oil, excuse me. Number 2 is the vegetable oil. So each oil will yield different types of biofuels, which is interesting. So we can really cater the needs of, or whatever needs we need to our starting materials, which is interesting. I'll skip over the mass of sodium methoxide, but the mass of the FAMEs, which stands for fatty acid methyl esters. FAMEs are the main component of biofuels, so that is how we gauge whether biofuels were created and to what extent they were created. So 2.92 grams is pretty arbitrary. But in the lab report, if you look, there's a technique of how percent yield is calculated. Percent yield is just a measurement of how much we expect to, how much biofuel we expect to make and how much we actually made. And it gives that as a ratio. So it's a pretty significant measure that I haven't provided here because it requires some knowledge of the calculations, which is presented in my lab report. So on this slide, you'll find the proton nuclear magnetic resonance I mentioned earlier. I go into a lot more detail in the lab report, but I can give some of the peaks. So on the x-axis, it says parts per million colon protons. So all this means is that it's a measure of protons at a specific chemical location, which all of this is described in the lab report. But for example, at the 5.3 mark, we have a peak of 0.26. That's representative of the starting material, which is not what we're looking for, but its presence indicates that our reaction did not completely go through, which is okay because we can't expect 100% of what we expect to be made. So there are several other peaks that are depicted in my lab report that I discuss later on in my lab report. So we'll go on to my plan moving forward. I will be rigorously proofreading everything, and that has been ongoing since last week, and it will keep going until Sunday. I'll be visiting the Writing Center on Wednesday just to present my paper, maybe get some feedback, and talk about what my peers have told me about my paper to this point. And then obviously the final lab report will be submitted on Canvas on Sunday. So that concludes my presentation. If you guys have any questions, suggestions, concerns about what was presented here, if you'd like to know more, if I can explain the proton nuclear magnetic resonance a little more, that'd be awesome. So just let me know. Feel free to email me at the email presented on this slide. And thank you all for listening.